So what are you made of? What is this screen made of? What is everything made of? For about the last 50 years, our best answer to that question is a theory called the Standard Model. It's basically the user's guide to our entire universe. And in this explainer, we're going to flip through it together. And, that is not an exaggeration. This model is an absolute powerhouse. It's the theory that told us, hey, go look for this thing called a gluon, or there should be a W and Z boson out there. And of course, the famous Higgs boson, decades before we could actually build machines powerful enough to find them. Its predictions are just so incredibly precise that it's become the bedrock of all modern physics. But to really get why it's so important, we have to rewind the clock a bit, back to a time of, well, chaos. Just try to imagine being a physicist in the early 20th century. New particles were being discovered so fast it felt like you were just collecting these bizarre animals for a zoo, but you had no idea how any of them were related. It was a mess, a beautiful, chaotic mess, and it desperately needed some kind of order. First, we had the familiar faces, right? The electron, then the proton. But the 1930s, that's when things got weird. We found the neutron and then the positron, our first real hint of antimatter. Before long, muons and pions were showing up to the party. As our machines got more and more powerful, the particle zoo was just overflowing. Physicists needed a zookeeper, and fast. That zookeeper turned out to be the Standard Model. So how did it tame this wild zoo? Well, it did something brilliant. It sorted every single particle of matter into just two families, quarks and leptons. That's it. Think of them as the only two food groups in the entire cosmic pantry. Everything you can touch is made from just these two types of ingredients. Now, the official fancy name for all these matter particles is fermions. They are the fundamental Lego bricks of reality. And that term you see on the slide, half-integer spin, that's just a really important quantum rule. It basically says no two identical bricks can be in the exact same place at the exact same time. It's the universe's no trespassing sign, and it's the fundamental reason you don't fall through your chair. And as far as we know, these bricks can't be broken down any further. And check out how elegantly these fermions are organized. They're all sorted into 3 generations. A good way to think about it is that each generation is like a heavier, much more unstable echo of the one before it. Generation 1, that's our world. That's the stable, everyday stuff. The up and down quarks, the good old electron, and the super elusive electron neutrino. And right there, that's the key. Those heavier second and third generations, they're incredibly fragile. They basically popped into existence for a split second in the fiery chaos after the Big Bang. And then poof, they were gone, decaying into the lighter, more stable stuff. Everything we see around us today, you, me, this planet, the stars, it's all built from the tough, stable survivors of that first generation. So what's the real difference between a quark and a lepton? Well, you can think of it like this. Quarks are the social butterflies of the universe. They are always found in groups, glued together by the incredibly powerful, strong force to make things like protons and neutrons. Leptons, on the other hand, they're the introverts. The electron, a lepton, is perfectly happy being on its own. And really, that's the whole deal. It's all about how they like to hang out. Okay, so we have our ingredients. We have our quarks and leptons. But a cookbook is pretty useless without the instructions, right? We need the forces, the rules of the game that tell these particles how to interact. And wouldn't you know it, the Standard Model has a whole other class of particles just for that job. Meet the bosons. If fermions are the bricks of the universe, then bosons are the mortar holding it all together. Their quantum rule, integer spin, is different. It actually lets them pile on top of each other, which is perfect for building up a force. Think of them as tiny messengers, constantly zipping back and forth between the matter particles, carrying little notes that say, hey, pull together, or push apart. Now, the Standard Model covers 3 of the 4 fundamental forces we know about. First up is electromagnetism, which covers everything from light to chemistry. That's carried by the photon. Then you have the strong nuclear force, the one that literally glues atomic nuclei together, carried by the perfectly named gluon. And finally, there's the weak nuclear force, which is responsible for some types of radioactive decay. That one's handled by these super heavy W and Z bosons. And then, of course, we have the superstar of the whole model, the Higgs boson. It's a really special kind of boson. See, it doesn't carry a force in the way we usually think about it. Instead, you have to imagine that the entire universe is filled with this invisible field, kind of like molasses, the Higgs field. As particles move through it, some of them get stuck and drag a little. That stickiness, that's what we experience as mass. Others, like photons, just zip right through without a problem, which is why they're massless.
Right. So, we've talked about the strong force, the weak force, and electromagnetism. But hang on a second. What about the one we feel every single day? What about gravity?
And with that one simple question, we find the cracks in this absolutely beautiful theory. Because for all of its incredible success, the Standard Model isn't the final answer. It's a brilliant map of reality for sure, but it's an incomplete one. And those blank spaces on the map, that's where all the action is in physics today. Yeah, for starters, it has absolutely nothing to say about gravity. Zero. It also incorrectly predicted that tiny particles called neutrinos have no mass, but we've since discovered they do. But its biggest blind spots are just massive in scale. The model is completely silent on dark matter, the invisible stuff holding our galaxies together, and dark energy, the mysterious force that's making our universe expand faster and faster. Add it all up, and that's 95% of the cosmos that our best, most successful theory simply can't explain. So where do we even begin to look for answers? Well, we build these absolutely enormous machines, like the Large Hadron Collider, and we do something that sounds almost ridiculously simple. We smash tiny little particles together as hard as we possibly can. These collisions are like tiny time machines, recreating the conditions of the Big Bang for a fraction of a second. And in the debris, physicists are hunting for clues, new particles, new forces, anything that could point the way to a better, more complete theory. The Standard Model is, without a doubt, one of humanity's greatest intellectual achievements. It gave us this breathtakingly accurate map of the known world of particles. But it also showed us the edge of that map, where the mysteries begin. And so, the biggest question in all of physics right now is a simple one. After the most successful theory in the history of science, what comes next?